So our first talk today is Francisco Alcaraz, and he'll be talking about generalization of free-parafermionic ZK Baxter quantum chain. Please.
Okay, thank you everybody for being in this talk. It's my pleasure to present this, remembering these masters that we lost recently, Baxter, that leave a lot of very interesting physics to us and examples. The talk I'm going to say is very linked to the idea of Baxter, because he produced the initial idea that followed many people to develop on this. So the title is the generalization of this free-parafermionic Zn and Baxter chains introduced by Baxter in 1985 and 89. This was most of the ideas here it was come from sharing collaboration with Rodrigo Pimenta and Jose Hoyos here in São Carlos. So the first question is what we mean by a fermion and a free-parafermion. Have to be specific. Actually, we have to remember when you take just a standard statistical mechanics undergraduate course and you go to the region of quantum gases, what you have, we have a sequence of energy level on particle level, and then we say that the energies can be just any combinations of those energy levels where they can be 0 or 1. You may be present or not. So this is what we call is just as a free fermion, or in general a free particle system. Actually, it's better to write this instead of write this energy like that. We make just make a global change in the energy levels by this constant here, and what we have essentially is the same energy here, but now with phases that numbers that can be 0 or -1, because you write just omega s e to the exponential 2π/2. And this s is 0, 1. So this is what we call fermions. So, and if you look for the partition function, Gram partition function of this, is just the product, independent product of those quasi-energy, these functions that depending on the quasi-energy. So the free nature came in this expression here. An example of realization of this interacting many-body problem, which has this expression, actually, is the quantumized model in the transverse field. So if you put the real value, real x here, imaginary x of the energies here are only real. So for simplicity, we just draw circles with radius equal to the quasi-energies, and this Hamiltonian is just written in terms of Pauli matrices, like that. This is the L-site chain. And those energies here, we have to compute putting one energy here or here. We cannot have both of them. So we have some sort of exclusion. So the Pauli principle somehow, it reflects in a circle exclusion. But it's a very interesting, simple circle. It's just a Z2 circle. And the energies here, in general, we can evaluate numerically, but for the spatial point when lambda equals 1, it's just this nice expression here. But what will be parafermions? Parafermions in the language will be what we call the parafermion here is just we have, instead of this Z2 circle, now we write the Zn circle. For n equal 3, we draw this type of thing. For n equal 4, like that. But it's important that always you have this circle repulsion. If you have a particle here, they cannot be here, or otherwise here we don't have also here. Okay. And oops. Okay. Now, So the energies are just this spatial summation here, where any levels you have to choose what position in this circle they have. This Si can be 0, 1 of n-1. So you see, you cannot have both particles in the same circle, both two particles in the same circle. And the Gram partition function is just the generalization of this right here, but here, as you see, the energies are complex. So these terms here are complex, but it's interesting. But although complex, this Gram partition function is real in this case. Okay. Now, a realization of that was given by Baxter in 1989, and actually this was somehow called the attention in the literature thanks to the work of Paul Fenley, that he realized and started to say, oh, this should have an explanation. And he did a lot of very interesting things in the model. And this just opened our attention to look for this model also. So the Hamiltonian now is just some kind of generalization of the transverse Ising model, but now instead of the polymetrics x, sigma x, sigma z, now we have some sort of Zn metrics. In general, they are n by n metrics that they satisfy this relation here, this Zn relation here, where now instead of plus minus 1 is exponential I to pi on n. So this model here, surprisingly, has this free particle spectrum that we just mentioned. And in the particular case, lambda equal 1, there also is analytical. This is the result. For example, for n equal 3, the z is just this matrix, and x is like that, and omega like that. So the question we start to look is that what is essential for fixing the eigenspectrum of this model, not to be free particle spectrum. So let us see in the Ising case. In the Ising case, the Hamiltonian is written like that, these two type of terms. So if we define energy density operator Hj, okay, we identify the odd ones as lambda sigma ij and the even ones sigma z, sigma I plus 1z. And then we realize that actually just they do not commute in this case, omega minus 1, if they are hi and hij are just distanced by 1. And otherwise, they commute. So this is the main algebraic information we have in the model here. If you look for the Zn Baxter chain here, if you do the same thing, you write this operator like before, which is generalization here of polymetrics. And what you realize is that, again, looking the commutation relations in neighbors, distance 1, we verify that instead of plus minus 1, is just this factor 2 pi over n, or it is exponential 2 pi, the root of the n root of unities. And this power is to the nc. Otherwise, they are 0. So what is important somehow here in this problem here is the fact that the distance that they do not commute are just distance 1. And there is the same kind of algebra. So essentially, this is the heart of this problem. Now, actually, then we can show that actually we can generalize this. We can consider more general models in which we introduce a parameter p, 1, 2, whatever, integer parameter p, where the Hamiltonian is like before sum of density energy operators, or if you want to say so, generator of an algebra, and they satisfy an exchange algebra like before, except that now instead of non-commuting just in nearest neighbor, now you can choose with this parameter p. Otherwise, they commute. So if you have this restriction in this algebra, this is enough to show that this model here are exactly integrable. In the previous case, it is the case where h to the power n is just a complex number, okay, like before. Example representations that have that is the, well, as we said, the Eisen case, a quantum Eisen model, which you can also write in a different way of representation. You take sigma x, sigma z, sigma x, 1, 2, 3, and the site 2, 3, zx, and so on, so on. Also, you have the same algebra. For p equal 2, you have this very interesting model, first introduced by Fenley. It's a three-spin models that the people call here disguised fermions. And the interaction like ZZX, ZZX, okay, they work like that. For p equal 3, we just extended these things here, okay? And this is the case of the fermionic case, n equal 2. For any general, the only thing you have to do is just promote your Pauli matrix to this Zn matrix. Sigma goes to Z and sigma x goes to X with this phase. And then we have a multi-spin generalization of the Zn Baxter free-parafermionic chain. Okay. Now, actually, even more extensions. A lot of some people have done a lot of extensions of that. Those models can even have free particle models in general frustrated graph that I do not say something about, I will not discuss here, but you can find a lot of very interesting works in the literature. Well, here I want to show, I'm concentrating one-dimension models. And what I can show that we can extend this model that one dimension that they have interaction for a certain distance p. Now we are going to consider that the commutation is not fixed. You have different distance. So for the thing we define generators as before, but now with a superscript, with another index, Ri, okay, where this Ri tells you what is the distance that of operators that they do not commute. Okay. And Ri is always bigger than 0. So your Hamiltonian as before is like that. Your generator has this other index. And it's very important. We can show that if this distance satisfies this condition, okay, the range of this has these conditions, okay, we are going to have a free fermion, free parafermion general models. So R is the range of interaction. In the interaction, these models came in the algebraic relation between them. So it comes like that. If you have one generator, Hi, Hj, okay, this has superscript Ri, then you have this, they don't commute with this phase omega, which depends on the n of the Zn model, okay? If the distance between J and I, okay, the distance is less than the Ri, the range of the guys on the left, okay? Otherwise, if bigger, they commute. So this is this. So if you look in a picture, previously the other models when you have the P models, P equal 1, 2, whatever, what you have in that case is have like lines, okay, all the places. So if you put Ri all the same, so it recovers this model here. So you have this P equal 1 models or P equal 2 models and so on. Now you can consider this more general RSOS pass in the interactions. So you can, for example, have this model here, no, 2, 1, 2, here. So the first one side range 2, 1, 2, 2, 1, 2. Here, this is another example here that we have 3, 2, 3, 3, 2. So if you do a picture of the non-commutative links of the interactions, the site 1 does not commute with the 3 guys on the right. So it doesn't commute here, here, and here. The site 2 with 2 guys. So here and here. The 3 with 3 guys, and so on. It's interesting that this condition here, I plus 1 bigger than I minus 1, imply that the range of interactions on the left of a given operator is fixed once you fix on the right. So you can compute them by this funny expression here, but anyhow you can compute. So actually, you can say, instead of say HIRI, you can say HILIRI, where RI gives you the distance of the density of operators that commute in the right, and the left this LI with the left distance. So if you look the commutation relation now in terms where we split these two terms, what you have is that the commutation relations is omega minus 1 for j minus 1 less than Lj, okay, and omega if j minus 1 is smaller than Ri, like we have before. Otherwise, is 1. So essentially, we have those operators given by this R. Okay. Representation is a general possible representation. Of course, you can have many, but a simple one that always you can do is if you try to representation the word basis. Suppose you just call by letters the generators. Given a general word will be composed by the powers of those generators here. So you have like in this way you have your vector space given by this. There are one-to-one correspondence with this object, if you think so. And if you apply just one operator like that, okay, because you know the commutation relations, then what you're going to have is just, if you work a little bit, is this product here with something with an I plus 1, okay? So this means that a possible representation you can have by that, well, if you just introduce, you consider the X and Z metrics, the Zn metrics, you realize that Hi is just this product of the Z matrix that starts on the left with the interaction, the branch in the left to I minus 1 of X. And so the Hamiltonian is like that. So this is what you have is a general range parafermionic model, which because of this restriction, we can show that actually it is a free parafermion. Sorry. Okay. Now, an example. Suppose you take n equal 2, so fermion. So you take this model, 2, 1, 2, 2, 1, 2, 2, 1. Okay. So we have this model here, H1. I just write the right one, okay? The right interaction, 2, 1, 2, whatever. One realization, possible realization, if I call this sigma 1 y, this sigma 1 x, sigma 2 1 z. If you do that, you realize actually this guy here does not commute because of they have the same index at the site, does not commute with that, does not commute with that. This one, but commute with that. This guy doesn't commute with that and commute with the other. And we can just write the links. And if you put together these terms here, write in a different way, this is just a standardized model with an additional field in y direction. So this is also a free particle. Actually, this is a trivial example because, okay, we can double this and do some Jordan Peterson presentation or even without doubling. Now, if you consider the case of general n, bigger n, so the Zn models, what you have is just essentially the Baxter chain here with another additional terms that plays the role of Zn extra surface field. So, how comes this integrability in general? Okay, it comes from this following factor. The Hamiltonian itself is just the summation of generators. And then you can build up, for example, a charge that we call charge 2 by summing all the products of these generators where each of the elements commute with the other. So this summation here. For example, if you have in this example here, so this is a 5 lattice with interaction 1, 2, 2, 1, 1. If you look the second charge, will be H1. So it has just one. He cannot be that. So H1, H3. Then you can have H1, H4, H1, H5. If you have H2, then the two of them they do not commute, but you have H2, H5, and then you have no more. So this is the charge 2 of your system here. And in general, you can produce the L charges are just the product of L generators such that each members commute among them, commuting. The number of the charges that you have, it's the number of them, we call M bar, and depends on the particular model you consider, the ranges that you have. But we can show that actually for any arbitrary thing, those charges are in evolution, so they commute among themselves. This expression. So if you go to m goes to infinity, okay, in principle, what we'll have is an infinite set of conserved charges. So in the model, in this sense, we normally call these models exactly integral. The question of being free particle models, this is crucial that you have some kind of inversion relation. So we produce a generating function, which is the summation of all the charges. It's a parameter u to the power L. And we can verify that in the Z2 case, if you multiply this inversion, these two generating functions like that, surprisingly, you have a lot of operators. Surprisingly, they cancel. We just have a scalar polynomial, which is u squared. In the Zn case, what you have to do is a Zn product of this with all these arguments. And again, you have this polynomial. So actually, you can verify easily that this charge satisfies a recursion relation like that. Okay, so one of in a given size and the charge are related in this way with this initial condition. And because of that, this implies a polynomial recursion relation among those polynomials. And this polynomial relation is very interesting. Now, the inversion relations, we can see that implies that the zero of these polynomials here will give you the quasi-energies in a free particle way. Like it will be something like that, but these energies here are related with the zeros of those polynomials that we generate by those recursion relations, and we have like that. And for each pseudo energy or each zero of the polynomial, okay, this expression here tells you that you have to choose just one of Si. So you have some for one, just exclusion like we have already discussed it. So if, for example, if you have this type of thing, put one particle here, no, this is not allowed. This is not in the Eigen spectrum. Okay. Now, the natural question is it possible to generate models is the same quasi-energy, but with no circle repulsion? Okay. Then we remember the connection that we have between the Eisen model, two Eisen model, and the XY chain. If you just have two decoupled Eisen model, like here in blue and red, and this Hamiltonian, and we can look the partner XY model like that, and or if you write sigma plus sigma minus sigma, this is the rise and lowering operator, and actually the spectra of those models are just related. So in the case of the quantum Eisen chain, you have this energy here. But in this case of the XY model, you can have any possibility here. So the spectrum of those models are the kinds of the XY or XX model, if you want to say so. It's just the two decoupled chains. Actually, this is general. We can do it for the XXZ chain. In this case, the correspondence of the fermionic is the Ashkin-Teller chain. Now, you can actually see what is behind it, construct more general models with no circle repulsion. This is done by generalization of this procedure before. We consider now models that written in terms of sigma plus sigma minus operator, and in such a way that if they go to the left, it's just by distance 1, but then when you go to the right, depends on an n. This n will be related with this n. And if you do that, for example, n equal 2 is just neighbor. So it's the standard Ising, so the standard xy, sorry. And this, for n equal 3, go 1, but jump, leaving one guy here. In general, you have that. And you have to put this string in the middle here. Okay. And if you do that, you have just, because you have sigma minus sigma plus, sigma minus, you have a U1 signature. So the Z component of the total magnetization commutator is the Hamiltonian. Okay. Now, this model, because they are bilinears, okay, if you do a Jordan-Wigner transformation, this will just give a bilinear, be bilinear inferno, and you know very well that this is solvable by the Jordan-Wigner. The Jordan-Wigner transformation can be solved by some sort of Bogoliubov transformation. This AJ like that is just the connectivity matrix related with the couplings that we had before. This n appeared because of this coupling of like distance. If you diagonalize this, the eigenspector of this is just the summation of all the possible energies can be 0, 1 in this case, and this lambda here is actually the eigenvalue of this the connectivity matrix. And if you define a polynomial u, which is just the determinant 1 minus au, okay, lambda is related with the eigenvalue of a, you can verify that you can take lambda k just asking for the zeros of this polynomial u, and then lambda k is 1 over u. So you need only the zeros of this polynomial that you are defining here, of this determinant. But determinants satisfy the Laplace cofactor rules. So you can get a recurrence relation for them. And if you work with this recurrence relation, you get the same kind of recurrence relation that we have before. And in this case, if you compare the other one, you verify that this P plays the role as n-1. So if you have exactly this expression here, okay, then you are going to have the same pseudo energies. So in the case of P equal 1, you have this correspondence Ashkentel and whatever. It's n equal, so if you have n equal 3, then you get a parafermionic version of the Fendley model, okay, n equal 3 and so on. So you have a huge families of XY model with sharing the same spectrum. If you, the other model, the Zn model, because look, here you can only have the n equal 2. To have the Zn model, there is a way to do it. You just consider cells of these interactions and you start to neglect some of those interactions. If you do that, you see that the recursion relations gives the Baxter chains. For example, for n equal 3, in the Baxter, you have this energy, this, and here you have all of them here in this multiplicity model. My time is going at the end. Just a remark of critical properties. In these cases here, it's interesting to tell that although the Hilbert space, m is the lattice size, is m to the power n, and the spectrum has a global degenerescence because you have only n bar charge, the charges, and n to the n. So it's extremely large degenerescences. And the model has, in general, critical points, multi-critical points. In the homogeneous case, the critical exponents are known. For example, the dynamic critical exponent is p plus 1 over n, and the specific heat is like that. You have some sort of universality class. When the model satisfies this condition, you have z equal 1, so you may ask for conforming variance. And in fact, you verify that you have, although the model are non-Hermitian, you have a model of conforming ones with central charge z equal 1. And also, it's curious that the equivalent of XY model in periodic lattice, they have very different properties. In the case of the inhomogeneous range model, this one that I told you before here, The multiple critical points will depend on the rates. So finally, observation, the simple curiosity of a single brilliant man like that, okay, drives the storms in several minds, I would say. Thank you, Ronald. You were just an example.
Do we have any questions?
Yeah,
Yes.
these are quantum chains. With the Hamiltonian, Baxter's Hamiltonian you show here on your slide, we know this corresponds to the chiropods as far as a two-dimensional classical model is concerned. With your generalization, all these generalization you've presented, they correspond to what kind of two-dimensional? What is the R matrix for the? What is the Young-Baxter equation for all your?
Yes. Actually, this should exist, but I do not know. We need to work on that. This is one
Future.
We'll leave for the people to look at. But you see, you have there is no reason for not having these things. Okay, you have this Hamiltonian will be the general Hamiltonian will be obtained by these general constructions also, because actually Baxter, I think, came from these ideas to arrive at the Hamiltonian, right?
Address Klumper.
Chico, is anything known about correlation functions? Let's say dynamical correlation function, or maybe to start with Brown state, static correlation functions?
Well, there is, what to say, actually, I didn't mention here, but although in those models here, you know the spectrum very well, there is a way, the eigenfunction is not, we do not know precise a way to do it. So I think we are still in a different, we need to know much more about wave functions of these things before to speak. Of course, in this case, the case, for example, that they are conform invariant, okay, we can say something that you should expect in the special parameter when you have p+1 equal n. But it's not, it's an open problem.
Thank you.
Let's take the speaker again.